Good afternoon, everyone. Yeah, thanks for coming to this talk. I am Alexander Demin. I am currently an undergraduate student in Moscow at HEC University. So I will talk to you about the new functionality in our package, StructuralIdentifiability.jl. The rough plan is that I will describe you what is the problem of structural identifiability, then we'll show you how you can analyze it using our package, and then we'll show you this cool new feature that you can now use. Right, so let's get started. So, roughly speaking, structural identifiability is a property of a dynamical model that determines if a parameter in the model can be recovered uniquely from the measured data. So let's say I'm a practitioner, I want to model some phenomenon in nature. I cook up some exponential growth model, right? So I write x of t, which is some process in time, and I write a, which is some time-independent unknown parameter. I conduct an experiment, I measure x of t. Now the structural identifiability answers the question if a, this unknown parameter, can be recovered uniquely from the measured data x of t. So in this particular case, you can see that, well, the parameter, there is just a direct formula. If we can measure the data ideally, and the derivative of the data can be computed without any errors, we can recover the value of a uniquely. So in this case, we say that the parameter is structurally identifiable. Okay, but let's now look at the opposite, at the interesting situation. So this example was probably quite unnatural. Right, so let's talk briefly about non-identifiability. The setting is absolutely the same. We still have some ODE, we have some process x of t, and time-independent parameters. Now there are two of them, right, a and b. So the question is the same as well, right? So can we recover the values of a and b from the data that we measure? So let's say we have some real world data, we conduct an experiment, we have a time series from 0 to 1 over t, and we measure some values x of t. Right, so the question what do you think, like, if values of a and b can be recovered uniquely from such data? So, well, just by looking at the equations, you can get a rough idea that if we swap the values of a and b around, the measured output actually doesn't change at all. So we can, in no way, from the point of view of the person who measures, we can distinguish different values of a and b from each other. So, and we can kind of, we can see this if we construct the graph in the following way. Right, so let's just take values of parameters a and b in some grid. So we take a and b in some square grid, and we plug them into ODE, we solve the ODE, and we can plot the error between the real data and the data that we have just estimated. Right, so on the graph on the slide, you can see basically on x-axis is the value of parameter a, on y-axis is the value of parameter b, and the color is the magnitude of errors that we get between the real data and the estimated data. So, and you can see on the graph that there are basically two symmetrical points, right? So two symmetrical sets of parameter values that give us the fit of roughly 10 to minus 25 error, which is almost 0. So one of these points is the point that I used to generate the data itself, this data in the time series. The other one is a spurious optimum that could hinder our practical identifiability analysis if we decided to use some optimization method with such a loss function landscape. So in this case, we would say that parameters a and b are structurally non-identifiable. Okay, so now to the package structural identifiability itself. The package was developed by Gleb Pogudin and Ruven Don several years ago. So later it was enhanced multiple times by Ilya Ilmer and other contributors. So the package supports modeling toolkit, supports formulations of problems with Catalyst, thanks to Torkel. And so the usage is fairly simple, right? You just import the package, describe the model in some simple domain-specific language, and you put, well, basically you put all your outputs that you observe in this y equals the output that you see. Now you can just pass the model to the assess identifiability function and get some nice output, some nice result. So let me just decipher the output on the screen a bit. So for each quantity in the model, we get some verdict. For x, in this case, we get globally, which means that the quantity is globally identifiable, everything is nice, we can uniquely recover the value of x of t for all possible t. But that is quite obvious because we measure it. So for A and B, situation is a bit worse. We only have local identifiability, which means that we can have up to finitely many different possible values for A and B, which is exactly what we have seen on the previous slide, right? Where we had at least 2 different points which give identically good fit. So one crucial thing that you can note from this slide is that you do not actually need any data to perform structural identifiability analysis, but it still can give you some useful information. So structural identifiability is a property of the model itself, in a sense. So in the light of the previous talks about practical parameter estimation, where it was mentioned how important it is to quickly iterate over building models, it can be quite useful to quickly reject some badly formulated models this way without conducting any experiments. But this is ancient history, so it is the classical identifiability analysis. So now let me show what was developed recently in structural identifiability, and so what can be used now. So structural identifiability now provides a new function, reparametrize global. This function accepts an ODE and outputs an ODE. This function tries to eliminate all non-identifiability of quantities that it can discover in the model. As a side bonus, this function can reduce the dimension of the model. So let's look at some example to see this more precisely. So here I have a standard SIR model studied a couple of years ago in the paper. So we have several states, several parameters, as the number of susceptible people, and so on. So we can call this classical identifiability analysis under 1 second on my laptop, get that, well, basically all of quantities, most of quantities are non-identifiable here. Okay, so the question is then, well, what we can do about this, right? So it's a fairly simple model, but still there is a lot of non-identifiability here. So this function reparametrize global basically accepts an ODE and spits out 2 useful pieces of information. Right? So you give it an ODE and it gives you back a transformation of your variables that you need to apply to the ODE to get some new ODE. Like on this example, you can see that well, for example, B divided by n times A was mapped to A3 and so on. Right, so the function basically tells you a transformation of variables that you need to apply. And then it also calculates the new ODE for you. Well, the variable names are a bit convoluted, but they can be recovered, of course, because they are in direct relation to the original ones. So you can notice right away that the new model has fewer parameters, right? 2 fewer parameters in this case. And, well, the additional nice thing is that all quantities in the new ODE are globally identifiable. So which was the goal from the very beginning. All right, so to conclude, non-identifiability, so the unappreciation of non-identifiability can impact negatively the practical parameter estimation. Structural identifiability provides a way to assess identifiability, and also provides these cool new features you can try out to reparametrize your model to kind of assist the practitioner to deal with this non-identifiability. Okay, I thank you for your attention. I'm done.
did you say it now supports full modeling toolkit models as well?
Right. Right, so it supports ODEs and discrete equations, so it doesn't support anything more complicated than that.
Like a-causal systems.
Uh,
So if you create a model through an a-causal, could you still perform the structural identifiability on it?
Well,
Yeah, I mean that was the StructuralIdentifiability.jl because you just end up with a differential algebraic equation system.
Yeah.
And then you can apply it to the flattened system. Yes.
Yeah.
mhm.
Yeah, so a-causal models right after structural simplification give you a flattened differential algebraic equation, and the structural identifiability tools do work with the DAs, right? They kind of write them in a slightly different form, but there's a translation process that is within the package that does that. Yeah.
Thank you, Chris. Yeah.